Hi, my name is Tom Hartka, and this lecture will be an introduction to p-values. This will cover some of the common statistical tests that we use to create p-values, and I'm going to demonstrate this using R. So if you haven't watched the previous video on some of the basics of R and Jupyter Notebooks, please go back and watch it. So let's get started. I think we all kind of have an intuitive understanding of what p-values are, but it's worthwhile going back and really thinking about what they mean, because that helps us figure out how to calculate them. So what is a p-value? Well, Wikipedia says in null hypothesis significance testing, the p-value is the probability of obtaining a test result at least as extreme as the result actually observed under the assumptions of that the null hypothesis is correct. And that's pretty much a mouthful. I think it helps to go back to thinking about our type 1 and type 2 errors. So type 1 errors that we're trying to avoid, that's false positive. That would be rejecting the null hypothesis when it's actually true. So that's what we'll be doing when we get a p-value. And we often set what's called an alpha level, which is our threshold. And if the p-value is less than that, we're going to say it's significant. If it's above it, it's not significant. A type 2 error, on the other hand, is a false negative where we fail to reject the null hypothesis when it's actually false. And that is not measured by the p-value. So let's do some examples. The first I want to do is to compare a single value to a normal distribution. So for this example, we'll think about a new patient arriving to the emergency department who has a temperature of 37.8. So, some people are very strict. You have to hit some certain level before you have a fever. So let's look at this example. So our hypothesis is that this patient's temperature of 37.8 is significantly different than the temperatures we see in healthy individuals. And what your hypothesis is usually trying to find a difference between what you observe, but difference between two groups. The null hypothesis is that our patient's temperature is not significantly different than those seen in the healthy population. So the first thing I want to do is actually just store our patient's temperature. So we are going to call that patient temp. Patient underscore temp. And again, the arrow is the assignment operator. We're going to say that is 37.8. Now let's create some, we're just going to randomly generate some data for our healthy population. So first we're going to set a seed. This just tells our, we're going to be using random numbers. So every time we run this notebook, if we set a seed, we'll get the same results. If we don't set a seed, every time we run it, we get different results. And then we're going to generate the healthy population. So we'll call this healthy underscore temps and assign that to a random sample of normal values. So we're going to call this our norm function. And we tell it how many samples we want. Let's say 10. The mean is 37 degrees and the standard deviation, say 0.5. And we can look to see what this gave us if we just say, look at values 1 through 10 in square brackets, it prints them down here. And we see we have all these kind of random values to many significant digits. And we can look at the histogram. All we have to do is call hist. And we'll do healthy temps. And we get this kind of random assortment of values. It doesn't really look normally distributed, but we know it is. But let's get some more values. And now we're starting to get a bell curve. So for this, we're actually going to use a huge sample. We're going to have 10,000 patients in our normal sample. So we have a nice smooth bell curve now. So now we want to find the number of healthy patients who had a temperature of 37 37.8 or greater. So let's look at this histogram again. And what I want to do this time is add a line representing our patient. So this V just says make a vertical line at, and I'm going to send it patient temp, which is a variable that has our patient's temperature. And then I'm going to say make this line red. So this is our population. This is our patient. So again, in null hypothesis testing, we want to know how many patients have our temperature or something more extreme. So let's look at everything that is 37.8 or greater and count up how many patients had a temp that was 37.8 or higher. So first, I'm going to create a variable to hold account of our patients. So this is the number of patients that were greater than or equal to our temperature. And I'm going to start with 0. And then we're going to move through all patients, all healthy patients. So it's for I, which is the variable that will hold the temp during each loop. So we're going to use an if statement to check if temp is greater than or equal to our patient. So if I, which is again each individual temperature, is greater than or equal to the patient temp, we're just going to add 1 to this. And we have to, after we add 1, we have to make sure we store it back to that same variable. So we're going to run through this. And now after we run through it, this patient greater than or equal to number should contain how many patients had a temperature of 37.8 or greater. And we see it was 540. And let's get that as a percent. Patient. And we're going to divide that by the length of our healthy temps. So it's 0.054. So this is basically an empiric way to measure a p-value. So our p-value for this would be 0.054. And remember, we're only looking at temperatures of our patient's temperature or greater. So this was a one-tailed test or one-sided test. But really, we don't know whether our temperature could have been greater or less than the healthy patients. So let's actually, what we want to do now is actually find anything that is either in this upper tail or this lower tail that is the same distance away from the mean. So the first thing we're going to do is get the mean for that healthy patient. So we're just going to type this function mean and send it healthy temps. And let's, I'm going to do this assignment and then have it print out the result. And it's just about 37, and that makes sense because that's the number we gave the random function. It's not quite, since these are random numbers. So what is the difference of our patient's temperature from the mean? Just type in patient temp minus the healthy mean. And again, we'll print it out to the screen after we calculate it. It's 0.8, so which is again what we expect. Let's go back and look exactly what we're looking at. We're going to add one more line. This time it'll be the healthy mean minus the patient's difference from the mean. So you see now we have two lines, and again, we're going to look at both these tails. So it's a similar loop that we're going to do. I'm going to just take this code and copy it. It's greater than or less than now. And what we actually want to check is for each temperature, we're going to see how far it is from the mean. And we're going to use absolute value because this could be negative. And it's actually now the temperature difference from the mean. So we'll change this to I_diff. So now every time for each temperature, it's going to see how far that temperature is from the mean, and it's going to compare it to how far our individual patient was from the mean. And then we used a slightly different variable, so we're going to increment this variable. Again, I hit Shift Enter to run this block of code. Let's see what we got. Now we have 1100, which is almost double what we got before, which makes sense because it's two tails now that are approximately equal. And let's change this into a percent. And we get now our p-value is 0.11, which is pretty far from the, if we use an alpha level of 0.05. So we would say we can't reject the null hypothesis. So this patient very well may be a healthy individual. So this is empirically doing it, making random numbers, actually counting who falls outside of the difference from our mean. We can do this statistically, though, which is the way that's commonly done. And this is called a one sample z-score. So the z-score is very simple. The z-score is just how many standard deviations our measurement is from the mean. So to get that, we're going to have to get the healthy standard deviation, and R has a nice built-in function to do that called SD. And we're going to send it healthy temps. And we'll print that out to the screen after we calculate it. And it's about 0.5, which is what we had asked the function to give us. So again, the z-score, it's typically negative. So I'm going to say negative patient diff divided by the healthy standard deviation. So that's our z-score. And typically what you do with a z-score, once you have the z-scores, you look it up in a chart, and that chart will tell you what the p-value is. The nice thing about R is that it can do that lookup for you with a function called p-norm. We send it z, lower tail equals true, and we get our p-values. P equals 0.546. So our p-value is 0.55, which is very similar to the 0.54 that we got with our empiric method. That's a one-tailed. To do a two-tailed, it's easy. We just multiply it by 2. And again, we get a number that's pretty close to the p-value of 0.11 that we saw. So again, both methods were rejecting our null hypothesis. What's even more common, though, is that we're actually comparing two different normal distributions. So, like a randomized control study, you'll have patients who receive the treatment, patient and control patients, and you want to compare those two populations. So let's do another example. So, what are there temperature differences between people with and without infections? So our hypothesis is going to be that there is a difference. When someone has an infection, the temperature is going to be different. And our null hypothesis is that there is no difference. We're going to do two different types of infection. So let's start with a bacterial infection. So we have temps for these patients. We're going to call our norm again. Also going to have a very big sample of 10,000. But now our mean is going to be 38.3, and our standard deviation is going to be the same, 0.5. And we can plot these on a histogram. So what I'm saying here is plot the healthy temperatures. The color do our red, green, blue, but 0 red, 0 green, all blue, but make it 75% transparent. So the opacity will be 0.25. We'll set the X limit, which is just the X and the X-axis limit to 35 to 40. And now we're going to do the bacterial temps. This time we're going to make it all red, but also only make it 25% opaque. And then I say this add T so that they're on the same plot. And this is what they look like. We see, just looking at it, it looks like there's probably going to be a difference there. But we're going to test this statistically. And to do that, you do a t-test. The t-test works when you have normally distributed data. The first person to describe it was it was a student's t-test written under the eponym student. And student was actually worked for Guinness Beer Company and was concerned with the quality of stout. What is built into R is the Welsh t-test, which is a little bit more generalizable. With the student t-test, both samples have to have the same standard deviation, whereas the Welsh has more flexibility. In our case, we could use either the student or the Welsh. So I'm going to call this function t.test, send it the healthy temps and the temps from patients who have the bacterial infection. And it gives us all this information, but really the critical thing is here is a p-value. And we see this is, it's got scientific notation here. So there are 16 zeros over here. So this is very, very significantly different. And the reason why is because we have huge samples. Let's make a different population, though. Let's say fungal infections. So we'll call it fungal temps. Again, we're going to make a normal distribution of data with, again, our giant sample. But this time, the mean is going to be 37. So in this theoretical population of people with fungal infections, it does not affect their temperature. Let's do the same thing we did above, but now we will call it fungal temps. And we see these are pretty much right on top of one another. And we can run our t-test again, but this time we're going to say fungal tense. And it is no longer significant. It's kind of surprising. It's as small as it is. If we reran this multiple times, we would get different numbers, and they would probably be around 0.5 on average. So why do we reject the null hypothesis? Why don't we focus on the hypothesis rather than the null hypothesis? And the reason is because we don't know the difference ahead of time. So let's do an example where we're going to run a drug study and see how our drug that we're developing affects patients' temperature. And we don't know what this is. So I'm going to say, just tell R to pick a random number from a uniform distribution, just one number from -1 to 1. So I don't know what the drug effect is. But drug temp will be, again, our standard normal distribution with an mean of 37 and a standard distribution 0.5, but we're going to add the drug effect here. Now we're going to do a t-test between the healthy population and those getting our drug. And we see it is significant. But we still don't know which direction it was significantly different. If we knew what the difference was going to be, we could compare what we expect to see with what we actually see, but that difference could be anywhere between -1 and 1. So we don't, if we tested a specific difference, we could say our data doesn't have this fixed difference from the normal population, but it wouldn't say anything about any other values for a difference. And when we actually look at our data, we see that it is a little bit lower than the healthy population. So instead of trying to guess what the difference is going to be, we flip it on its head. We say we're going to test the null hypothesis, and if there is a difference, that will confirm our hypothesis. So if you read the American Statistical Association, they say a p-value is not a measure of the probability that the studied hypothesis is true. That's exactly right. I mean, again, we're looking at the null hypothesis and not the hypothesis. The second thing they say is the p-value is not the probability that the data were produced by random chance. And honestly, I think this is a bit pedantic. Really, like what we saw before when we randomly generated data, like when we had a p-value of 0.55, about 0.55% of the data by chance was above that p-value. There are some slight differences, but I honestly don't think that this is a bad way to think about what a p-value is. Another important thing is that the p-value doesn't measure the size or importance of the result. So if you have a tiny difference in temperature, but you have 20,000 samples, you're going to have a very significant p-value, but whether that's clinically relevant is, you have to determine that as someone interpreting the data. So in summary, remember, the p-value tests the compatibility of the data with the null hypothesis. They must be interpreted in the context of the study and in the context of previous medical knowledge. If you're going to compare one sample to a normal distribution, that's a one sample z-score. If you're going to compare two normally distributed populations, that's a t-test. And that's all for this video, and I will see you on subsequent videos. Thanks.